Good morning to all. Myself Arun, pursuing PhD under the guidance of Dr. Sundaravadivel. I am going to present my research thesis titled on simple cooking of carbon dioxide and its hybrid for environment and energy applications. And I welcome my external experts, Dr. A. Selvam sir, Senior Scientist, Livestock Processing Division, CSIR IAP Data Room, and Dr. D. Murugan sir, Principal Scientist, Department of Caters, CSIR CLRI, Adayar Chennai. And these are my academic details, and these are the coursework which are suggested by DC members. And the outline of the presentation. Chapter 1 gives introduction. Chapter 2 experimental part and analytical technique. Chapter 3, 4 and 5 are my working chapter. Chapter 6 summary and conclusion. And chapter 1 gives a brief introduction about carbon dots, heavy metal ion sensor, supercapacitor and solid state synthesis of metal oxides. And the first what is carbon dioxide? It's a new category of carbonic material with a zero-dimensional size with average particle size of below 10 nanometer, and it was accidentally discovered by the scientist Zhu in the year of 2004 during the purification of single walled carbon nanotube. After the discovery of the carbon dioxide in the year of 2004, it was developed a lot in the basis of synthesis strategies and the application. Such as electrocatalyst, supercapacitor, bioimaging, drug delivery, and wearable sensor, and so on. And the classification of carbon dots. The carbon dots are classified into majorly 3 different types based on their structure and composition. The first one is graphene quantum dot, and the second one is carbon quantum dot, and third one is carbon-based polymer dots. After that, metal containing carbon dots are a newcomer to the family of carbon dot, which has an enhanced property when compared to its bare carbon dots. And the preparation of carbon dots. Carbon dots are prepared by either using chemical or biomass material which contain carbon atom. Similar to the nanoparticle synthesis, carbon dots are also synthesized via top-down and bottom-up approaches. And the top-down approach involves the nano-cutting of bulk carbon resources such as fullerene, graphene, nanotube, graphite, etc. via laser ablation, electrochemical, and all discharge method. And the bottom-up method corresponds to the preparation of carbon dots with the help of small organic precursor molecules via ultrasonic, hydrothermal, and micropyrolysis method. Micro-assisted synthesis of carbon dioxide is one of the easy and very famous method to prepare carbon dioxide because it offers localized heating, rapid preparation, low cost in the production, scalability in the product, environmentally friendly in nature, and produce uniformity in the particle size. And the properties and application of carbon dioxide. Carbon dioxide are well known for its multiple properties such as tunable photoluminescence, excitation dependent spectra, outstanding photostability, up-converted photoluminescence, excellent biocompatibility, high water solubility, smaller in size, and electrical conductivity, and well-functionalized surface. Because of its multiple property, carbon dots have been employed in various research areas such as solar cells, LEDs, supercapacitors, bioimaging, photocatalysis, and sensor, and so on. And the mechanism of fluorescence carbon dioxide. Still now, the exact mechanism of fluorescence in carbon dioxide is a debate. However, the researchers reported 3 different possible mechanisms, which are quantum confinement effect. The different emission from the carbon dioxide are observed from the different particle size in the solution, and the surface defect corresponds to the existence of defect and different multiple functional group. In the carbon dioxide leads to multiple emission columns, and the carbon core and molecular state defines the hybridization between the defective inner core and well functionalized surface group on the surface of the carbon dioxide. Water pollution. Water pollution is one of the significant global issue that affect ecosystem, human health, and overall quality of life. Actually, the major reason for the water pollution is heavy metal ions, organic dyes, industrial chemicals, pharma compounds, and pesticides, microplastics, and radioactive materials in the water. And there was a report said that already 80% of our nation's surface water became polluted, and it creates a demand to access the safe and clean water. And heavy metal ion contamination in water. Actually, the water was contaminated by the excess use of agriculture pesticides, mining process, industrial waste, volcanic eruption, electronic waste dumping into the water sites, and it directly affects the human body via food chain. And this directly causes kidney damage, cardio issues, damage to bones, liver malfunction, skin disease, respiratory issues, disturbed cellular function, and so on. And the World Health Organization set an permissible limit that how much of metal ion should be present in the drinking water, which are listed here. And the carbon dioxide as a fluorescent probe. However, there are several fluorescent probes are available, such as organic dyes, quantum dots, fluorescent proteins, metal nanocluster, and so on. But carbon dots have something special property which holds less toxicity, easy preparation, high quantum weight, high water solubility, easy functionalization, outstanding photostability, and excellent biocompatibility. Next, supercapacitor. Supercapacitors are also known as electrochemical capacitor, which stores charge and offer high power density rate via fast charging and discharging rate with long cycle life. And the supercapacitor classified into three different types based on its charge storage process, which are electrical double layer capacitor, pseudo capacitor, and hybrid capacitor. The advantages of supercapacitors are it offers higher power density, fast charge discharge rate, lower internal resistance, maximum life cycle, and highly safer to operate. And the uses of supercapacitors are electric vehicles, portable electric devices, power backup system, and solar and wind power storage. Metal oxides for supercapacitor application. Generally, metal oxide has mostly used as an electrode in supercapacitor because it has a high specific capacitance due to its redox behavior and good electrical conductivity due to the existence of multiple oxidation states, and offer very good cyclic stability due to its structural stability, and low cost due to higher abundance in nature, and offer higher power density and structural tunability. Some commonly used metal oxide as electrode in supercapacitor are manganese dioxide, cobalt oxide, nickel cobaltate, Fe3O4, TiO2, and nickel oxide. The conventional method and the demerits of metal oxide synthesis. There are wide variety of number of synthetic metals methods are available to prepare metal oxide, which are small gel process, biological method, flame spray pyrolysis, microemulsion, co-precipitation, hydrothermal, solvothermal, and chemical vapor deposition method. However, this method has several disadvantages such as less scalability in the product, requirement of additional reagent, post-preparation treatment, consumes lots of energy, non-safer in nature, and consumes lots of time, and consumes excess of solvent during the purification of the product. So that we have moved to an alternate strategy to prepare the metal oxide via solvent-free solid-state synthesis method, and it offers low cost in the production and gives more scalability in the product, less post-treatment work, eco-friendly in nature, and solvent-free condition, saves lots of time, and does not require any additional reagent. And the International Union of Pure Applied Chemistry has also recently highlighted that mechanochemistry is one of the chemical technology that will change the world. And the chapter 2, experimental part and analytical technique. These are the chemicals and equipments I have used to prepare the material, and these are the sophisticated analytical techniques that I have used to study the property of the prepared material. And the chapter 3, multifunctional carbon from simple precursor and excellent heavy metal ion sensor and aqueous environment. Synthesis of carbon dioxide. The carbon dioxide synthesis with the help of ethylene diamine and ethylene glycol with the help of micro irradiation at 700 watt for the time period of 10 minutes. And the yielded carbonized product of carbon dioxide dissolved in water, it gives a bright blue color emission at 364 nanometer and dull emission at 254 nanometer excitation light. And the optical properties of carbon dioxide studied. The figure A represents the UV visible spectra of carbon dioxide. Here we can observe two different absorption peak, 270 at and 345, which correspond. The 270 nanometer peak corresponds to the pi to pi star transition occurred in the sp2 carbon in the carbon dioxide, and the 345 nanometer wavelength corresponds to the N to pi star transition occurred in the various multiple functional group exist on the carbon dioxide. And the figure B represents the photon emission spectra. Here you can see that while exciting 242 300 nanometer, here you can see the excitation dependent spectra, excitation independent spectra with the maximum emission wavelength of 330 nanometer. And while exciting 332 470 nanometer, here you can see the excitation dependent spectra with the maximum emission wavelength of 425 nanometer. And the figure C normalized PL, which further confirms that the excitation independent spectra from the carbon dioxide is observed from the core state of the carbon dioxide, and the excitation independent spectra will observe from the surface state of the carbon dioxide. And the structural property of carbon dioxide. The figure A represents the XRE spectra of carbon dioxide. Here you can see the broad peak centered at 23.42 degree theta with a 002 plane, which further confirms that the carbon dioxide, which is an irregular graphitic structure with amorphous in nature. And the figure B represents the TEM image of carbon dioxide, the average particle size distribution of 5 nanometer. And the figure C represents the high resolution TEM image of carbon dioxide with a de-stressing value of 0.33 nanometer. And the FTR and zeta potential are shown here. Figure A represents the FTR spectroscopy plot. Here we can see that it confirms the presence of OH, NH, CN, C11C, CO, and CH moieties in the carbon dioxide, and the zeta potential profile confirms that the carbon dioxide which is in negative surface charge with a value of minus 0.9 millivolt. And the XPS shown here, figure A represents the survey spectrum of carbon dioxide with the confirmation of C, carbon, oxygen, and nitrogen moieties atoms, and the figure B, C, and D further confirms the existence of C1s, N1s, and O1s and their corresponding functional moieties. And from the observed UV, PL, and XPS spectra, we have proposed a structure that carbon dioxide holds an defective inner core followed by well functionalized surface structure. And the stability of the carbon dioxide. And the carbon dioxide possesses very good stability under the ionic strength from the concentration of 0 to 200 millimolar addition of NaCl and continuous photo radiation of continues under the photoradiation up to the time period of 60 meters. While the PL intensity of the carbon dioxide is reduced at the acidic pH, it may be caused due to at the acidic pH condition, the delocalization of electron was hindered. And the sensing property of the carbon dioxide studied with various metal cations from that chromium and mercury are selectively detected by the carbon dioxide, which is shown in figure B. And this figure A and D represents the quenching plot of carbon dioxide with the chromium and mercury with the concentration of 0 to 200 micromolar addition, and the figure B and E represents the PL intensity of carbon dioxide versus concentration of chromium and mercury, and the figure C represents the linear fit plot of carbon dioxide detection of chromium with the R-square value of 0.99 followed by the calculated LOD of 0.09 micromolar, and the figure F represents the linear fit plot of mercury detection with carbon dioxide. Here the R-square value of 0.98 was used to calculate the LOD of mercury with a range of 0.16 micromolar. And the sensitivity of the carbon dioxide was evaluated with the addition of various metal ions with the mixture of carbon dioxide and carbon dioxide with chromium and mercury separately, and the sensitivity plot represents that the carbon dioxide hold very good sensitivity. And the detection mechanism, the figure A represents the PL quenching plot of carbon dioxide with the mercury addition. With the increasing concentration of mercury, we can see the shift in the PL emission spectra, which confirms that the process was happened by the photoinduced electron transfer mechanism, and it is actually due to the transfer of electron from carbon dioxide to mercury ions. And figure B further confirms that figure B represents the precise overlap of excitation and excitation spectra of carbon dioxide and the absorption of chromium, which further confirms that the detection mechanism was inner filter effect, and it has actually happened by the reabsorption of excitation wavelength of the carbon dioxide by the chromium ions in the aqueous solution. And the portable sensor probe was fabricated with the help of normal and normal Wattman filter paper by embedding carbon dioxide into the two different filter paper. Here the figure A and B represents the visual detection of mercury from the concentration of 0 to 200 micromolar addition, and the figure C and D represents the visual detection of mercury from the concentration of 0 to 300 micromolar addition with the help of carbon dioxide embedded two different filter papers. And the summary of this work, the core and surface emitting carbon dioxide was prepared with an average size of 5 nanometer through simple precursor using household microwave method. And the multiple emissive states of carbon dioxide were evaluated with the UV, PL, and XPS technique. The prepared carbon dioxide process excitation dependent emission and high stability under various circumstances, and the PL behavior was effectively used to detect 12 metal ions with very good detection limit. And the glowing character of the carbon dioxide was employed to detect the toxins visually through paper-based fluorescent probe. And this work was published in Collection Surface Physicochemical and Engineering Aspects. And the chapter 4, simple synthesis of water soluble lithium carry carbon dioxide as the admirable probe for improved environment application. And the preparation of ruthenium carry carbon dioxide are shown here with the help of ethylene diamine and ruthenium chloride under the micro irradiation of 700 watt at 4 minutes of time period. The dark brown color product was applied which is dissolved in water, and it shows a bright blue color emission. And the ruthenium free carbon dioxide was prepared with the help of ethylene diamine with the same procedure. And the optical properties of ruthenium carry carbon dioxide and carbon dioxide are shown here. The figure A represents the UV visible plot of carbon dioxide and ruthenium carry carbon dioxide. Here the two different peaks are observed in the carbon dioxide, which corresponds to pi to pi star and n to pi star transition. And the ruthenium carry carbon dioxide also expresses two different absorption peak, which corresponds to pi to pi star transition, and the peak position at 448 nanometer, which confirms that the metal to ligand charge transfer spectra further confirms that the existence of ruthenium in the matrix of carbon dots, and the figure B represents the photoluminescence spectra of carbon dots with the excitation dependent emission behavior with the maximum emission wavelength of 424 nanometer, and the figure C represents the ruthenium carrying carbon dot with the maximum emission of 460 nanometer. Here also the ruthenium carrying carbon dots expresses excitation dependent emission behavior, and the figure D represents the normalized PL. Here we can see that after the existence of ruthenium, we can observe the shift followed by the reduction in the PL intensity. And it was further confirmed with the lifetime analysis. The figure E represents the carbon dots with the average lifetime of 7.02 nanosecond, and the figure F represents the average lifetime of ruthenium carrying carbon dot with the 9.36 nanosecond. And this result confirmed that after the introduction of ruthenium, the carbon dot matrix which improves the excited state lifetime by reducing the recombination rate. And the surface studies of ruthenium carrying carbon dots and carbon dots are shown here, and figure A and D represents the surface spectrum of carbon dots and ruthenium carrying carbon dots, which confirm the presence of carbon, nitrogen, ruthenium atoms in both the preferred material. And figure B represents the C1 spectrum of carbon dots and confirms the corresponding functional group. And figure E represents the C1s and ruthenium 3D high resolution XPS spectra. Here the peaks of ruthenium 3D 3/2 and ruthenium 3D 5/2 further confirms the existence of ruthenium in 2+ oxidation state in the carbon dots matrix. And the figure C and F represents the N1 spectra of carbon dots and ruthenium carrying carbon dots. Here the ruthenium carrying carbon dots N1 spectra experiences a shift in binding energy when compared to the carbon dot spectra in the pyrrolinic, pyridinic and graphitic nitrogen, which further confirms that these are the active moieties which involves the stabilization of ruthenium 2+ in the carbon dots matrix. Next, the FTR and the zeta potential plots. The figure here represents the FTR spectra. Here we can see after the introduction of ruthenium, the peak position of NH was shifted toward red, which further confirms the XPS result. And the figure B and C represent the zeta potential plot here, that where carbon dot shows a negative surface value of -11.7, and the ruthenium carrying carbon dot shows a positive surface charge of 3.19 millivolt, which further confirms the existence of ruthenium in the carbon dots. And the structural studies of ruthenium carrying carbon dots and carbon dots are shown here. Figure A represents the XRD plot. Here we can see that after the existence of ruthenium, the XRD shift was observed from 22.6 degree to 27.7 degree, which further confirms the existence of ruthenium in the lattice position of the carbon dots matrix. And figure B represents a TEM image of carbon dots with average particle size of 5.06 nanometer, and figure C represents the HRTM image of carbon dots with the average D spacing value of 0.33 nanometer, and figure D represents the TEM image of ruthenium carrying carbon dots with the average particle size of 6.04 nanometer, and figure E represents the D spacing value of ruthenium carrying carbon dots with 0.34 nanometer, and the figure F. The comparative Raman spectra further confirms the existence of ruthenium, which induces the structural defect, which was confirmed by the shift in graphitic and defective carbon in the carbon dots and ruthenium carrying carbon dots. And the stability of the ruthenium carrying carbon dots was further evaluated from the carbon dot shows. This ruthenium carrying carbon dot shows very good stability under the ionic concentration from 0 to 200 millimolar of NaCl, and the continuous photo irradiation of 60 minutes, and storage time period of 0 to 30 days. But this under the pH condition, at alkaline condition, the carbon dot shows reduction in the pH intensity, which may be due to the ruthenium 2+ in the carbon dot matrix was converted into nanoparticle at alkaline pH. And the sensing property of ruthenium carrying carbon dots was evaluated with the different metal cations and anion. From the checked different metal cations and anion, chromium and mercury, chromium 6+ and mercury 2+ are selectively detected by the ruthenium carrying carbon dots, and it was further evaluated. The figure A and D represents the quenching plot of ruthenium carrying carbon dots with the concentration of 0 to 150 micromolar addition of chromium and mercury, and the figure C represents the linear fit plot of ruthenium carrying carbon dot used to detect chromium metal ion with R² value of 0.99. The LOD was calculated as a 0.128 micromolar, and figure F represents the linear fit of ruthenium carrying carbon dot used to detect the mercury ion, and with the R² value of 0.98, the LOD was calculated as 0.328 micromolar. And we have also checked the detection behavior of bare carbonate along with the chromium and mercury ions. Here the figure A and B represents the quenching plot of carbonates with the chromium and mercury, and the figure C represents the LOD value of chromium detection was 4.5 micromolar, and the figure F represents the detection of mercury LOD value as 4.8 micromolar. It confirms that the result shows that the existence of ruthenium in the carbonates matrix, which improves the detection capability of the dual metal ions, and the sensitivity of the ruthenium carry carbonates was evaluated with adding various metal cations and anion with the mixture of ruthenium carry carbonates with chromium and mercury individually, and this plot further confirms that with a blank it further confirms that the ruthenium carry carbonates have very good sensitivity among the detection and the confirmation of the detection process. The figure A represents the precise overlap of excitation spectra of ruthenium carry carbonates with the absorption spectra of chromium 6+, which further confirms this process. This quenching was happened by inner filter effect mechanism, and the quenching process was a dynamic quenching process. It was confirmed by the lifetime analysis with the change in excited state lifetime with ruthenium carbonates with chromium. And figure B represents the excitation and absorption spectrum of ruthenium carry carbonates and chromium and mercury ions, and followed by the figure D represents the excited state lifetime of ruthenium carry carbonates with mercury, which further confirms the static quenching process happened during the quenching, and this result suggested that the detection was happened by the inner filter effect mechanism. And the detection mechanism was further elaborated with the pictured image, and the inner filter effect was actually happened by the reabsorption of wavelength by the chromium in the solution, which observed the excitation wavelength of the ruthenium carry carbonates, which further reduces the emission property of the ruthenium carry carbonates. And the photoresist electron transfer mechanism was happened by the transfer of electron from mercury 2+ ion in the excited state. And the paper-based portable sensor was fabricated with the help of water and filter paper by embedding ruthenium carry carbonates with the filter paper to detect the toxins. We have visually from the concentration of 0 to 200 micromolar addition. Here we can see the visual detection of chromium metal ion, and from the concentration of 0 to 300 micromolar of concentration of mercury. Here also we can see the visual quenching of ruthenium carry carbonates with increasing concentration of mercury 2 ions. And the summary of this work: ruthenium carry carbonates are prepared with a simple, effective, and micro-assisted process with the quantum yield of 19.21 from the UV, XPS, FDR, and Raman spectral technique. It was confirmed that ruthenium in the carbonates matrix exists in a stable ruthenium 2+ oxidation state, and the ruthenium carry carbonates PL behaviors effectively utilized to detect dual metal ions with a good detection limit through different PL mechanisms. And the ruthenium carry carbonate shows a good selectivity, sensitivity, and stability against different environmental conditions, so that the ruthenium carry carbonate's embedded filter paper visually detect the carcinogenic pollutant with a low cost fabrication. Because of the higher water solubility and extended excited state lifetime, it was utilized as a potential material for biological and photocatalytic application further. And this work was published in Materials Today Chemistry Journal, and the chapter 5, carbon dioxide, a multifunctional nano-sized gene tool for the physical reformation of nickel molybdenate in solid state for enriched energy storage application. And this slide shows the preparation of carbonates, nickel molybdenate, and a nickel molybdenate carbonate hybrid. The carbonates are prepared with the help of diaminopropane with paraformaldehyde by heating in the microwave at the time period of 10 minutes with 700 watt. And the nickel molybdenate was prepared by simple grinding solvent-free synthesis method by simple mixing of nickel and molybdenate precursor followed by calcination at 400 degrees Celsius. And the nickel molybdenate carbonate hybrid was prepared with the help of by adding different concentration of carbonates with the nickel and molybdenate precursors followed by calcination. The interesting result observed from the after the synthesis was the bare nickel molybdenate, which shows an one-dimensional rod structure, which is further increasing the concentration of carbonate, which was totally changed into sheet-like morphology. And the studies of carbon dioxide. The figure A represents the invisible spectrum of carbon dioxide with the N to pi star transition, and the figure B represents the acceleration dependent emission property of carbon dioxide with the maximum emission level of 434 nanometer. And the figure C represents the exotic spectrum of carbon dioxide with the amorphous in nature, and figure D represents the DEM image with the average particle size of 4.3 nanometer of carbon dioxide and 0.33 nanometer of d-spacing value. And the figure F represents the zeta potential graph. Here the minus 8.49 further confirms the carbon dioxide exists in negative surface charge, and figure G, H and I represents the C1s, N1s and O1s spectra of carbon dioxide with the confirm the corresponding functional group on it. And the XPS spectra of nickel molybdenum and nickel molybdenum carbon dioxide hybrid. The figure A represents the nickel 2p spectra. Here you can see that the nickel 2p 3/2 and nickel 2p 1/2, which further confirms the existence of ruthenium nickel, which is in 2+ oxidation state. And the figure B represents the high resolution spectra of molybdenum 3D. Here you can see that molybdenum 3D 5/2 plot and spectrum, and molybdenum 3/2 spectrum further confirms the existence of molybdenum 6+ oxidation state. While comparing the nickel molybdenum XPS spectra of nickel and molybdenum with the nickel molybdenum carbon hybrid, here you can see the huge shift about 1 electron volt in the binding energy value, which is actually happened by the strong electrostatic interaction between the carbon dioxide with the nickel and molybdenum precursor during the synthesis, which actually modulates the electron density around both the nickel and the molybdenum precursor. And the figure C represents the O1 spectra of nickel molybdenum and the nickel molybdenum carbon hybrid, which confirms the presence of metal hydroxy, metal oxygen metal and lattice oxygen in the both the prepared material. And the figure D represents the N1 spectra of nickel molybdenum carbon hybrid. The presence of CW1N spectra further confirms the existence of carbon function group with the nickel molybdenum carbon hybrid. And the structural properties of nickel molybdenum and the nickel molybdenum carbon hybrid are shown here. And the figure A represents the exotic spectra, and which represents the nickel molybdenum and with the different concentration of nickel molybdenum components are shown here. And the bare nickel molybdenum, which matches with the JCPS odd number, which is shown here. And the interesting result was observed here with the increasing concentration of nickel molybdenum with the carbonate, with the different concentration of carbonate addition with the nickel molybdenum precursor, the peak intensity was reduced, which further confirmed the reduction of crystalline behavior, and after the introduction of carbonates was confirmed. And the figure B Raman further confirms that introduction of ruthenium, which induces the defects in the nickel molybdenum structure with the reduced intensity in the Raman. And the figure C represents the ESF spectra of the increased intensity at the G value of 2.005 further confirms the existence of more number of free electron in the nickel molybdenum carbon hybrid when compared to the bare nickel molybdenum. And the figure D represents the bed surface area analysis. Here the bare nickel molybdenum gives a bed surface area of 124.074 meters square per gram, and the nickel molybdenum with the carbon hybrid gives a 163.287 meters square per gram. And the interesting and the result is this is the first report that this much of huge surface area was observed with the bare nickel molybdenum, and it was observed by and it was obtained by the solid state grinding method. And the structural properties of nickel molybdenum carbon hybrids are shown here. And the figure A represents the DEM image of nickel molybdenum with carbon hybrid, the average particle size of 20 nanometer. And the figure C represents the HR term image of nickel molybdenum carbon hybrid, which further confirms the existence of nickel molybdenum and carbon dioxide with the corresponding d-spacing value. And the figure D represents the SAD pattern of nickel molybdenum carbon hybrid, and it further confirms that presence of polycrystalline nature of the nickel molybdenum carbon hybrid. And the figure F represents the semi-elemental individual mapping of nickel molybdenum carbon hybrid. Here it confirms the presence of nickel, molybdenum, oxygen, carbon and nitrogen moieties on it. And the formation mechanism. From the observed result, we have proposed a formation mechanism that how one-dimensional nanorods was changed into sheet-like morphology after the introduction of carbonates was evaluated, and it was represented as while grinding the nickel and molybdenum precursor with the negatively charged carbonates, which starts to make a strong electrostatic interaction with the nickel and molybdenum precursor. It actually modulates the electron density around both the metals. After the regular nucleation process begin, the conventional growth process of one dimension was altered towards two-dimensional method, two-dimensional way via C and B axis, and it was further confirmed in the SEM analysis. And the electrochemical properties was carried out, and the figure A to D represents the CV profile of nickel molybdate with a different concentration of carbon dots from the scan rate of 10 to 100 millivolt per second. And the figure E to F, T to H represents the galvanostatic charge discharge profile of nickel molybdate and nickel molybdate carbonate hybrid. Here we can see that nickel molybdate with 15 mg of carbonate possesses a high specific capacitance value with 1947 farad per gram. And the combined electrochemical property shown here. The figure A represents the combined CV spectra of nickel molybdate with a different concentration of carbon dots. Here we can see that nickel molybdate with 15 mg of carbonate gives a very good current response when compared to the other. And the combined GCD shown here. Figure B represents the nickel molybdate with 15 mg of carbonate, which shows an extended charge discharge character. And the figure C represents the ES spectra, which shows the nickel molybdate with 15 mg of carbonate which have a low resistant and high charge transfer rate. And the cyclic stability was well weighted up to the 1000 number of cycle. After 1000 number of cycle, the nickel molybdate with the carbonate hybrid shows a 97.7% of capacitance retention, and the nickel molybdate shows only 77.7% of capacitance retention. And the charge storage mechanism was further evaluated with the power law. The figure A represents the linear fit plot of cathodic and anodic peak. The observed R square value of 0.98 confirms the charge storage process was diffused controlled process. And the figure B, and with the B value of 0.42 confirms the charge storage process with the diffusion controlled process. And the figure C represents the capacity and diffusion process from the concentration of from the scan rate of 1 to 5 millivolts per second. The capacity behavior was increased, and the figure D represents the done real plot. Here you can see that 82.2% of capacitive process and 70.8% of diffusion contribution was achieved at the scan rate of 5 millivolts per second. And the possible reason for electrochemical character enhancement in the nickel molybdate carbonate hybrid was listed here. It is actually achieved by the 2D morphology from one dimensional to the change in morphology from one to two dimensional morphology, less crystalline nature, good functionality, enhanced surface area, modified electronic structure, highly active functional groups, and improved electrode-electrolyte interface with the existence of carbon dioxide. And we have prepared asymmetric capacitor with the help of Swetchlock cell and using nickel molybdate carbonate hybrid as a cathode and activated carbon as a anode. And the figure A represents the corresponding CD spectra, and figure B represents the GCD spectra of the asymmetric device with the 140.6 farad per gram at 1 ampere per gram of current density. And the figure C represents the capacitance retention of 92.5% after 1000 number of cycle. And the figure D represents the Aragon plot with the energy density of 43.9 watt hour per kilogram and power density of 3711 watt per kilogram. And the summary of this work: compounds with multifunctional properties were synthesized through simple micro method with average size of 4.3 nanometer. The smaller size, well-functionalized carbonates provide a new path to synthesis morphology tailored nickel molybdate with a one-step solvent-free solid-state reaction condition. The fabricated material with the carbon dioxide exhibits an outstanding electrochemical charge storage property, and which has a greater specific capacity, which is 3 times higher compared to its bare nickel molybdate. The prepared electrode offers a very good energy and power density, and this presented result indicates that this present fabrication type of this material open up an alternate path and fills the research gap in the fabrication of the electrode material for supercapacitor. And this work was published in Advanced Sustainable System. And the chapter 6, summary and conclusion. Actually, the ultimate aim of the work is unveiling the multiple properties of carbonates. Using in that work, first work we used ethylene glycol to prepare carbonates, and it shows core and surface emitting property. And in second work, the ruthenium carrying carbonates, the carbonates in the ruthenium which stabilizes the ruthenium 2 in the carbonates matrix and makes it highly soluble in water. And the third work, the carbonates from the paraformaldehyde and the diamopropane was prepared with the micro method, and the morphology and it was used as a morphology tuner, functionalizer, surface area enhancer in the nickel molybdenate preparation, which was prepared via solid state method and it is used as a supercapacitor. And these are the list of articles published and communicated and the co-author publications and the list of conferences attended and the acknowledgement. I thank my supervisor Dr. Sundaravadivel for his constant support and encouragement. I thank Professor Dr. M. Adanariswari, HOD Department of Chemistry, PhD, and Professor B. Napoleon, Dean Research, Professor Dr. C. John Tiruvadigal, Chairperson, SRMST, and I thank Doctoral Committee members, Professor Dr. S. Anandan, Department of Chemistry, IIT Trichy, Dr. B. Muthuraman, Department of Energy, University of Madras, Guindy Campus, and External Examiner, Dr. G. Satyaraj Sir, Scientist, CATS, CLRI, ADAYA, and SRMST for providing research fellowship and research facilities, and special thanks to Mr. S. Sarathkumar and Dr. A. Nagarajan from University of Madras, and my seniors, junior friends, lab mates, and my family members. Thank you.